Good morning. Welcome to Krishna's classroom. So we look at the well-known Lebesgue theorem in this talk. Let us recall what we have earlier proved in this regard, or a related result. We have shown that if f is a real valued increasing or monotone function on interval AB, then f is continuous almost everywhere on. We have proved this theorem earlier. At that time, we were looking at the continuity of monotone functions. And this says that the points of discontinuity is a set of measure 0. That is the points of discontinuity or the function is continuous almost everywhere on the interval. So in this talk, we go one step further and look at the problem of differentiability of such functions. So differentiability of monotone functions. So the theme is differentiability monotone functions. So what we prove is that if f is a real valued monotone function on the interval AB, then it is differentiable almost everywhere. Okay. So that is the theorem. This is the Lebesgue theorem. If the function f needless to say it is real valued, then only you can talk about monotonicity, is monotone on the interval AB, then it is differentiable almost everywhere on AB. Now this means that the set of points where it fails to have a derivative is a set of measure 0. Okay. So that's this is the statement of the theorem. That is, a set of points where such a function fails to be have a derivative is a that's what you mean by it is differentiable almost everywhere. So it goes one step further from this. Of course, it is wherever the function is not continuous, then of course it is not differentiable. But there may be points where the function is continuous but may not be differentiable. So what this second theorem tells is that the set of the function f, if it's a monotone function, then where the derivative does not exist is a set of measure 0. Okay. So let us prove this theorem. So we construct a proof. So without loss of generality, we assume that f is an increasing function. So you see this is because, see, the function is a decreasing function, then you can always consider minus f. In that case, minus f is increasing. So whatever we prove in this case will be applicable to minus f. And that would mean that if minus f is differentiable almost everywhere, then f is differentiable almost everywhere. So that's straightforward. Okay. Also, we assume AB is bounded. Now, what one does in this case, in the case of an unbounded interval, if this interval is unbounded, then what you do is you write it as the union of an ascending sequence of bounded intervals. Okay? And then for each one of these intervals, whatever we prove is true. And then just make use of the continuity of what is called the M star or the outer measure. Okay? So let us work on that. Right. Otherwise, that means if the interval is not bounded, then we can express AB as the union of countable collection of an ascending collection of bounded intervals. For instance, if you take minus infinity to plus infinity, then you can write it as the union of minus n to n, the bounded interval minus n. So this, for example, this is what I mean. So if you take minus infinity to plus infinity, you write as union of n equal to 1 to infinity. Each one of this is bounded. So that's not difficult in that case. So any bounded interval, you can use an intersection of this. Okay. If E is an unbounded interval, then you can write this as the union of minus n to n intersection. That they are all going to be bounded intervals. So we can express AB as a countable union of an ascending sequence of open bounded intervals. Therefore, whatever we prove here can be applied to each one of them. Now, what you have to prove is that the measure of, or the outer measure of, the set of points where the function fails to be differentiable is equal to 0. So once the measure of the set is 0, then you see that m star is equal to m. That is there. But let us see how we proceed this. Then we use the continuity of Lebesgue measure on this sequence. Because on each, see what you have is this, see that you get a set of points where the function fails to be differentiable for each of these bounded intervals. And this would give you the set of intervals, the set of points E where the function fails to be, where En is contained in En plus. This is the property that you have for n equal to 1. And therefore, what happens is that because of this particular property and the property of M, you have measure of E, the Lebesgue measure of E is equal to limit n tending to infinity of measure of En. And you know that each of this is 0 and therefore 0. So that's how you prove this. So this is what you mean by using the continuity of the Lebesgue measure. Therefore, we have reduced the problem now to working on what are called open bounded intervals. Okay, so let us now So what do we mean by they are the function has a discontinuous derivative? Because we have seen the upper derivative and lower derivative exists at every point. And you know that the function fails to be differentiable if the upper derivative is not equal to the lower derivative. So we are looking at points where the upper derivative and lower derivatives differ, and we also have the inequality that the lower derivative is less than the upper derivative of f at any point. So this is what you have. So we know that the points where f fails to be differentiable are those points where the upper and lower derivatives differ. So what we are up to is looking at these points. So we are looking at the set say E, set of all x belonging to such that the lower derivative f at okay. What we have to prove is that equal to 0. Okay, so that's our strategy. So now we write the following. Let E alpha beta be defined as the set of all points x belonging to AB such that d bar f greater than alpha, greater than beta, greater than now you see that if they differ, because the upper derivative of f at x is greater than the upper derivative of the lower derivative of f at x, you see that there is a gap between them, and therefore there exists alpha and beta, numbers alpha and beta, such that d bar f is greater than alpha, is greater than beta, is greater than d sub bar f at x. Okay, so we mark such points. We fix alpha beta and mark such points, and we call that E alpha beta. Okay, that means this is the one. Sorry. For some particular x. So every x you can have this kind of thing. So such points you mark out, fixing alpha and beta. Now we choose alpha and beta as rational numbers. So you see that such rational numbers do exist. So what next? Therefore, what we conclude is that this collection is a countable collection, because alpha and beta are rational numbers. This collection E alpha beta is a countable. We are not saying that this set is countable. What we say is that E alpha beta, that is the set of all x belonging to AB, for which this is true. This is a countable collection of sets. That is Q being countable. Now we analyze this. Now we observe that the outer measure M star is a countably subadditive function. Hence, it is sufficient to prove that E alpha beta, measure of M star of this is equal to 0. Okay, so that you see the entire set of points where you have where the derivative does not exist is a union of such sets. Okay, and this is a countable collection, and M star is a countably subadditive function. Therefore, you see that if each one of this is 0, then the total thing is 0. That's the argument that we make use of. So set. Now we fix alpha beta and do this. This is for the sake of brevity while writing. We use this notation. So let This is not the same E that I was using earlier. Let epsilon be positive. Now we can choose an open set O such that E is contained in O, which is contained in AB, and measure of O is less than the outer measure of E plus epsilon. So, see, what it says is that you can approximate it. You can pack the whole thing E inside an open set, and the measure of O is less than m star of E plus epsilon. This means the following. See, I just use this, the Venn diagram rather than the real line stuff. So what I have is, if this is E, then I can put it inside an open set O such that, and since it's an open set, the outer measure of O is the same as the measure of O. See, because it is measurable. Therefore, measure of E plus epsilon for any epsilon. So that says you can approximate this E as closely as you want through open sets. We are going to make use of that. Here we make use of simply the definition of outer measure. Okay. So look at how the outer measure is defined. Okay. This follows from what it is the following. How do you define the outer measure? The outer measure is defined as the infimum of the measure of open sets O, where O is a superset of E. That's the whole thing. And because of that infimum, you are able to get for any epsilon, you are able to get a corresponding O such that the measure of O is less than measure of m star of E plus epsilon. Let's write this as a block. We shall need it and denote this by 1. Okay, now let script F be the collection of closed bounded intervals CD contained in O such that FD minus Fc is less than beta. Beta is the same beta that you are using here. So you recall you have this beta, alpha. So we had this. This is d bar f. E sub bar f. Okay. So it is this beta that we are using. Beta times d minus c. Now this here we have used the previous result. This is what we have proved last time. Okay. So since less than beta on E, what you can have is that there exists, or what you have is the collection F. How we have defined? F is the collection of all bounded closed intervals CD in this such that this is less than. Such collection is a Vitali cover is a Vitali cover is E alpha beta. Okay. Therefore, I mean that's quite easy to see. Therefore, what more you can infer from this? The Vitali covering lemma now assures that there exists a finite disjoint subcollection closed interval CKDK, say k equal to 1 to n of f such that mesh m star of E slash is less than epsilon. That says that you can take out a finite collection of closed intervals whose union, if it is taken out from E, what remains has outer measure less than epsilon, the epsilon that we have already used earlier. Now this is also a vital result that we use. Okay. Now by the choice of CKDK, the intervals ck dk, we have union of contained in O. It's a subset of O. Okay. Further, this is also what you have. In this is less than dk minus ck, because on each of these intervals ck dk we have the similar same inequality holding. Okay, right? And this, you know, is further less than or equal to beta times measure of O. Because of this particular property, these are disjoint intervals, and you know that this is contained in O. These are disjoint intervals. Therefore, this is less than or equal to beta times measure of E. Measure of because O is measurable, therefore it is outer measure is the O is open, therefore outer measure is the same as N star. Or yeah, outer measure is the same as its measure. This, you know, is excellent because it comes from the first inequality that we have used. Okay. Now we use using the previous lemma, that is the theorem that we have proved just before proving this in the last lecture, that is in lecture 56, we have proved a theorem. See, for 1 less than or equal to k less than or equal to n, we have, this is the inequality, you have outer measure of E intersection yeah, this follows from that the way in which we have chosen alpha and beta. Therefore, what we have is m star of E is less than or equal to sigma k equal to 1 to n m star of E intersection ck dk plus epsilon which is less than or equal to 1 upon alpha. Use this inequality f sigma ck epsilon, and this of course is less than or equal to beta upon alpha, because we are now going to make use of this inequality. Beta upon alpha m star of E, we use this inequality, this particular inequality, m star of E plus epsilon for each choice of epsilon. This is true. Okay. Therefore, what do we have? Now you know that since m star of less than infinity, finite, and beta upon alpha less than 1, we have 1 minus beta upon alpha and this is true for since this is true, and 1 minus is positive, we have that is m star of E can be made as small as you please by choosing epsilon. Okay. Therefore, this is, we conclude that m star of E is equal to 0. Discontinuity. of f is not differentiable, is a set of if it is outer measure 0, then it is measure 0. So all sets of 0 outer measure are measurable, and the outer measure is equal to measure. So that concludes the proof of this. Now what we want to remark, this result best possible. Now this we established by proving that we need some construction work. It's already available in literature. Okay. So if zero for any set E of measure 0 contained in the open interval AB, there exists an increasing function on AB with which fails to have differentiability at these countable Okay, so that's what we can do, and there's the example by appearing in the book by Rees and Nash, which is given as that is functional analysis by Rees and Nash, where the example is given as an exercise in this in this particular book by Roydon. Okay, so let me just give the problem. So let leave it to you to explore this. Let E be contained in R with a measure of equal to 0, and E is contained in interval AB with measure of equal to 0. There exists a countable collection of open sets, open intervals contained in AB countable collection for which each point of infinite many intervals of this collection and measure of finite. That means the intervals that you choose is such that dk minus ck, this series converges. Now define, this is the definition of the function, fx to be equal to length of this set for every x belonging to Then F is monotonically increasing and fails to be differentiable sorry, this countability is not quite. So set of measures 0, that's enough. It's differentiable at each point in. Because you know that there are sets whose outer measure is 0 even without being countable. So I remove that from it. Okay? That condition is not. Is set of. Okay, so that is a example which is this is discussed in detail in the book on functional analysis by Reason Nash. Okay, thank you very much, and we'll continue with it in the next lecture. Right.